Aeroponics.
Aeroponics is the process of growing plants in an air or mist environment without the use of soil or an aggregate medium. The word aeroponic is derived from the Greek meanings of aero and ponos. Aeroponic culture differs from both conventional hydroponics, aquaponics, and in vitro growing. Unlike hydroponics, which uses a liquid nutrient solution as a growing medium and essential minerals to sustain plant growth, or aquaponics, which uses water and fish waste, aeroponics is conducted without a growing medium. Because water is used in aeroponics to transmit nutrients, it is sometimes considered a type of hydroponics.
Methods.
The basic principle of aeroponic growing is to grow plants suspended in a closed or semi-closed environment by spraying the plant's dangling roots and lower stem with an atomized or sprayed, nutrient-rich water solution. The leaves and crown, often called the canopy, extend above. The roots of the plant are separated by the plant support structure.
Benefits and drawbacks. Increased air exposure.
Air cultures optimize access to air for successful plant growth. Materials and devices which hold and support the aeroponic-grown plants must be devoid of disease or pathogens. A distinction of a true aeroponic culture and apparatus is that it provides plant support features that are minimal.
Benefits of oxygen in the root zone.
Oxygen in the rhizosphere root zone is necessary for healthy plant growth. As aeroponics is conducted in air combined with microdroplets of water, almost any plant can grow to maturity in air with a plentiful supply of oxygen, water and nutrients. Some growers favor aeroponic systems over other methods of hydroponics because the increased aeration of nutrient solution delivers more oxygen to plant roots, stimulating growth and helping to prevent pathogen formation. Clean air supplies oxygen, which is an excellent purifier for plants in the aeroponic environment. For natural growth to occur, the plant must have unrestricted access to air. Plants must be allowed to grow in a natural manner for successful physiological development.
Other benefits of air, CO2.
Plants in a true aeroponic apparatus have 100% access to the CO2 concentrations ranging from 450 ppm to 780 ppm for photosynthesis. At 1 mile 1.6 kilometers above sea level, the CO2 concentration in the air is 450 ppm during daylight. At night the CO2 level will rise to 780 ppm. Lower elevations will have higher levels. In any case, the air culture apparatus offers ability for plants to have full access to all the available CO2 in the air for photosynthesis. Growing under lights during the evening allows aeroponics to benefit from the natural occurrence.
Disease-free cultivation.
Aeroponics can limit disease transmission since plant-to-plant contact is reduced and each spray pulse can be sterile. In the case of soil, aggregate, or other media, disease can spread throughout the growth media, infecting many plants. In most greenhouses, these solid media require sterilization after each crop and, in many cases, they are simply discarded and replaced with fresh, sterile media. A distinct advantage of aeroponic technology is that if a particular plant does become diseased, it can be quickly removed from the plant support structure without disrupting or infecting the other plants. Due to the disease-free environment that is unique to aeroponics, many plants can grow at higher density plants per square meter when compared to more traditional forms of cultivation.
Water and nutrient hydroatomization.
Aeroponic equipment involves the use of sprayers, misters, foggers, or other devices to create a fine mist of solution to deliver nutrients to plant roots. Aeroponic systems are normally closed-loop systems providing macro and micro environments suitable to sustain a reliable, constant air culture. Water droplet size is crucial for sustaining aeroponic growth. Too large a water droplet means less oxygen is available to the root system. Too fine a water droplet, such as those generated by the ultrasonic mister, produce excessive root hair without developing a lateral root system for sustained growth in an aeroponic system.
Nutrient uptake.
The discrete nature of interval and duration aeroponics allows the measurement of nutrient uptake over time under varying conditions. Atomization greater than 65 pounds per square inch 450 kilopascals, increases bioavailability of nutrients. Consequently, nutrient strength must be significantly reduced or leaf and root burn will develop. Plant growth and fruiting times are significantly shortened when feed cycles are as short as possible. Ideally, roots should never be more than slightly damp nor overly dry. A typical feed pause cycle is less than 2 seconds on, followed by 1.5-2 minute pause 24/7. However, when an accumulator system is incorporated, cycle times can be further reduced to less than 1 second on, 1 minute pause.
Low pressure units.
In most low-pressure aeroponic gardens, the plant roots are suspended above a reservoir of nutrient solution or inside a channel connected to a reservoir. A low-pressure pump delivers nutrient solution via jets or by ultrasonic transducers, which then drips or drains back into the reservoir.
High-pressure devices.
High-pressure aeroponic techniques, where the mist is generated by high-pressure pumps, are typically used in the cultivation of high-value crops and plant specimens that can offset the high setup costs associated with this method of horticulture. Since the late 2000s, home indoor gardeners have had access to simple high-pressure aeroponic HPA systems at affordable prices. High-pressure aeroponics systems include technologies for air and water purification, nutrient sterilization, low-mass polymers and pressurized nutrient delivery systems.
Aeroponic propagation, cloning.
Aeroponic culturing revolutionized cloning propagation from cutting of plants. Firstly, aeroponics allowed the whole process to be carried out in a single, automated unit. Numerous plants which were previously considered difficult, or impossible, to propagate from cuttings could now be replicated simply from a single stem cutting. Aeroponics has now largely surpassed hydroponics and tissue culture as means for sterile propagation of plant species. Due to the automation of most parts of the process, plants could be cloned and grown by the hundreds or even thousands. In short, cloning became easier because the aeroponic apparatus initiated faster and cleaner root development through a sterile, nutrient-rich, highly oxygenated, and moist environment.
Less nutrient solution throughput.
Plants grown using aeroponics spend 99.98% of their time in air and 0.02% in direct contact with hydroatomized nutrient solution. The time spent without water allows the roots to capture oxygen more efficiently. The reduced volume of nutrient throughput results in reduced amounts of nutrients required for plant development. The relatively low solution volumes used in aeroponics, coupled with the minimal amount of time that the roots are exposed to the hydroatomized mist, minimizes root-to-root contact and spread of pathogens between plants.
Greater control of plant environment.
Aeroponics allows more control of the environment around the root zone, as, unlike other plant growth systems, the plant roots are not constantly surrounded by some medium.
Improved nutrient feeding.
A variety of different nutrient solutions can be administered to the root zone using aeroponics without needing to flush out any solution or matrix in which the roots had previously been immersed. This elevated level of control would be useful when researching the effect of a varied regimen of nutrient application to the roots of a plant species of interest. In a similar manner, aeroponics allows a greater range of growth conditions than other nutrient delivery systems. The interval and duration of the nutrient spray, for example, can be very finely attuned to the needs of a specific plant species. The aerial tissue can be subjected to a completely different environment from that of the roots.
More user-friendly.
The design of an aeroponic system allows ease of working with the plants. This results from the separation of the plants from each other, and the fact that the plants are suspended in air and the roots are not entrapped in any kind of matrix. Consequently, the harvesting of individual plants is quite simple and straightforward. Likewise, removal of any plant that may be infected with some type of pathogen is easily accomplished without risk of uprooting or contaminating nearby plants.
More cost-effective.
Aeroponic systems are more cost-effective than other systems. Because of the reduced volume of solution throughput discussed above, less water and less nutrients are needed in the system at any given time compared to other nutrient delivery systems. The need for substrates is also eliminated, as is the need for many moving parts.